Good morning, students, and welcome to the another session of Structural Analysis 2. I hope you are all doing well fit, and doing good. Also, learning the ongoing contents on your own. And I hope that today you have brought your writing tools with you so that whatever exercise that we are going to carry out today in this class or lecture, that you can in parallel you can do it at your end also. In between, if required, I'll be asking few questions to any of you. Being a volunteer, you can answer, and please start entering your details in the chat box so that we can go ahead with the attendance. Now, friends, this is the last session for the fixed beam analysis. Right. So I advise all of you to focus, concentrate, and just try to get the gist of the concept. However, we have already started the discussion analysis, and we also have noticed that fixed beam, being the rigid structure, it's very useful, advantageous, material savvy, and efficient. And there are a couple of limitations as far as the analysis methods are concerned that also we have observed. Like in case we so far we have discussed two principal methods. Those are useful to analyze fixed beams. These methods are one is the moment area method and second is the Macaulay's method. And in the last session, if you recall, we have discussed that if you have standard load cases for the fixed beams, then there should not be a problem. Then there is no hurdle about calculating the friction moments for the fixed beams, right, with the help of area moment method. But in case of the complex loading, or not complex exactly, but if it is varying in nature, if it is not symmetrical in geometry as well as in loading intensities, then there may be a challenge. There may be a kind of long calculations, complex calculations, or may not be appropriate to obtain the overall diagrams, exact diagrams, geometrical shapes of this kind of loading conditions. And in such cases, Macaulay's method proves to be the better solution method. And that is what we have seen also in the last session. So again, today's session is dedicated for the numerical examples and exercises. And in a next session, I shall be teaching you how to analyze another type of indeterminate structure that is called continuous beam. So in next week, we are going to begin with the continuous beam. So today we are going to conclude almost the fixed beam as a indeterminate structure. One point I wanted to share with all of you that usually we know that there are three reactions at fixed and conditions. However, in case of the absence of the horizontal forces, you can reduce it to two. One is moment and second is vertical force. So in that case, when the horizontal force is completely absent in case of the fixed beam, we can say that the fixed beam is statically indeterminate to 2 degrees, right? Because 2 plus 2, 4 reactions, and we have two conditions of equilibrium because we are avoiding sigma h as a condition available, because since there is no force in horizontal direction, you can reduce it to 2 only. So this is just a point. And if you answer that SI of the fixed beam is 3, that's completely fine. Should not be a wrong answer, right? But this is, I wanted just to, you should know that this is the another way of looking at to the conditions. Now, you can see that we have already discussed all these points. And in the last session, we solved this problem with the use of the Macaulay's method, which is very well known to us. we have done many practices, numerical exercises based on the Macaulay's method. So today's session is dedicated to, first of all, the loading condition, which is not symmetrical, so that how to get the answer for that, because uh, it is difficult to prepare the diagram of the complex unsymmetrical loading. This was the last slide that we discussed in the last session, where I demonstrated how you can utilize the typical shapes of the bending moment diagrams of the simply supported beam, which are rendered from the fixed beam by using the principle of superposition, right? So while you are using principle of superposition, let us say, right right here you can see it is shown that you have to separate the beam in at least two or whatever three conditions. Like here you can see, according to the type of the loads, we have first of all obtained the simply supported beams according to the individual loading, right? So then third part is the only moments which are applied as friction moments on this structure. So you can very well notice that we are capable easily to draw all the bending moment diagrams of all the standard cases. Then later on, you can merge or club these areas together as capital area 1, let us say, and this becomes your area 2. And then you know how to proceed. You can add these two areas together according to the intensity of the forces, intensity of the loads. You can obtain the maximum value of this bending moments in both cases, let us say point loads and the UDL. So you can then have area sub area, let us say A1 equals to, in this case it is 1/2 BH, and here in this case sub area 2, that is 2/3 of BH, right? So when you club A dash 1 and A dash 2, it gives you A1, right? And A2 is very much obvious to calculate, like MA or MB into total length, right? So then when you compare it, it gives you readily your value of either MA or MB. And once you have any of the moments and the reactions, where in case of this symmetrical loading, it is again very easy to obtain the reactions directly by assuming it as simply supported beam. So at that time already you have analyzed reactions. So the only pending task is to obtain moment. And since the loading is symmetrical, both end moments will be equal, right? So in short, you can finish this type of symmetrical loading conditions of the fixed beams with less time and energy. However, today I have planned to explain you how you can obtain the friction moments for non-symmetrical loading, and we will also see some important points when meanwhile when we'll be calculating it. So I insist that if you have your writing tools with you, you can develop this question along with me in your notes. So let's go for it. All right, so this is your fixed beam condition. Both ends are fixed, right? Now we have first force at, let us say, 1 meter distance, okay, from point A. Then we have, let's say, a UDL, right? So that is also at a distance like this, right? And let's write down the values together. So it is 60 Newton, and here in case of UDL you have value of 10 Newton per running meter. And let's name the beam accordingly. So this is your and A, this is your B. Just for a sake of clarity, we are naming this another points like C and D. Okay. Now, as you can observe, as I told you earlier in the previous sessions also, that please observe the question carefully before you start or before you make your mind to use a particular method. See, there is nothing wrong to use moment area method again in this case as well. You can definitely develop your simply supported beams for point load only, then simply supported beam for UDL only, and then you can develop your bending moment diagram for fixed end moment. But as you can notice, here the loading is not symmetrical. I will be giving you the distances. So based on that, you can understand that there is definitely unsymmetry in the given condition. So let us say this is 1 meter. Okay. This is again 1 meter. Okay. And then you have 2 meters. Okay. This is 1 meter. This is again 1 meter. So you can see that 2 meters with UDL gives you 40 kilonewton almost, 40 Newton almost, and 60 Newton is located nearer to support A. So obviously the reaction of the this end will be definitely larger. So when you have force nearer to the support particularly and it is larger than the other force, definitely the friction moment will also not be similar to the other end. So we cannot expect this diagram or this sort of diagram of the fixed end moments in this case. I hope you are getting my point, right? So this cannot be the case in this. So when there are uncertainties, when there are non-surety, then what to do? Then the best practice is to go along with the Macaulay's method, which is more general, more accommodating, and more flexible to address the complexities of the numerical. So with this briefing, let's start. Let's see how to solve. There is a critical point which I would like to discuss with all of you in this case of the types of the problems. If you recall, even if you want to use the Macaulay's method, what we used to do is we used to calculate the reactions first, right? But that was in the case where you can easily obtain your reactions. Now supposing this is the condition and I want to develop my simply supported beam like this. Okay, I'm just explaining you why we should not first obtain the reactions. So right now we have applied the forces. Right. So you can see that it's now a typical MOS kind of problem, mechanics of solids problem, where if you take moment of all the forces about this point, you can get the reactions definitely. But if I don't want to do it at the beginning, right? And second thing is when the moments are not same, right? Then what to do? Then you have to obtain the slope equation as well as deflection equation. So that is the core point, or that is the central point or focus point of this exercise which I'm going to share with you. You will see that how we address and treat this numerical for complete solution. So you don't need to worry about the reactions at the beginning. Let's start. So the first step is to draw the free body diagram. Yes. So that it gives you clarity what are the forces required to be considered, right? Along with the nomenclatures VA, VB. Okay. Then we have point loads and we have a sort of UDL. Okay. And these are the reactive moments. Support moments, fixed moments, whatever you want to call it. Let's say MA and MB. And of course, you have the values with you so that you can add over here. You do have distance with you, 1 meter, 1 meter, and 2 meter. All right, so now we are going to use Macaulay's method. Why? Because there are two major reasons. One is loading is not symmetrical. Second is it is difficult to develop a superposition of the bending moment diagrams of such complex loading since the end moments are not symmetrical. Definitely end moments you will see that they are varying in nature. Okay. So the next step is, if you clearly understand this type of problems for one shot, it will be, then the game of practicing only. So I don't focus on number of numericals to be solved, but whatever we solve, we should solve it in complete respect, right? That means overall grasping should be obtained. So right now you focus on the discussion. M is, or let us say mx is the generalized bending moment that we are going to, bending moment equation that we are going to develop here. So uh, let's travel with, let's change the color. Let's travel with x distance from point A. Okay. And let's write down the equation. So MA is anti-clockwise. I will consider it positive. So MA, right. Then VA into X, so minus VA into X, because you know that we have considered clockwise moment as negative. Then we have new family member, that is 60 Newton, right, in our journey from A to B. So we know according to the Macaulay's method of generating the equation, we will place its sign first and then we'll separate it. So we have 60 Newton, and if I extend this X, it will be somewhere here. Right. So it will be creating again the anti-clockwise moment. So it will be positive. So plus, then let's put this, division, and 60 into x minus, what is the distance? 1 minimum. So x minus 1. Is it okay? Now when we come into the another frame of D to B, this was the area between C to D, and we developed this equation. Further, if we look at to the D to B area, we have a UDL, and you know how to develop the equation for UDL for when the X is reached in this region. So let me separately draw it. Let's say here, this is your UDL. Okay, and from point A still X has reached here, but the UDL starts from this point and ends here, so that is 2 meters. So I'm standing here just to randomly take my section over here. So what should be the distance here? X minus 2. This is a UDL. So we do have intensity. So intensity in the length. So intensity is 10. Length is x minus 2 because x is larger than 2. So 10 into x minus 2 is the total load, and the half of the length, that means half of x minus 2 will be the effective distance, and that will be creating again the anti-clockwise moment over here, right? So again I will put plus sign over here. uh, 10 is the force intensity into x minus 2 square by 2. All right, so that is what is the perfect equation for us. Now we are going to use this for our slope deflection typical equation. So here EI d square y upon dx square equals to minus mx. So here our governing equation is going to take shape over here finally. EI d square y upon dx square equals to uh, this is ma plus vax, right, minus 60x minus 1 minus, let's say, 10. Let's keep it as it is. Otherwise, you can convert it to 5 also, no issues. Just for a time being. Okay. So this is what is our final starting point. So fourth step will give us the equation for, let's say, slope first of all. So slope equation that we have to obtain with the help of this equation. So EI d square y upon dx square. Sorry, let's start integrating it here itself, right? There is no point of rewriting the equation. So first time when you integrate this particular equation gives you slope. So ei dy by dx, ma negative ma becomes max plus va. You can rearrange this term also for positive start also, but however it doesn't make any difference. Va x square by 2 minus 60 x minus 1 square upon 2 minus 10 x minus 2 cube upon 6. All right, so this is our first slope equation. So this is to be preserved. So we'll write it as a slope equation. That's it. Slope equation. Now, please keep doing this with me because I'll be asking you the answer, right? Randomly also. So this is a slope equation that we will keep on a secured side. Now let's apply the boundary conditions. Which are the boundary conditions? X equals to 0, let us say. So we forgot to add constant, right? Don't make this mistake in exam, please take care. So it's fine that we have added it here, but technically it should come in the beginning, very beginning itself, when your next dashed portion starts, right? However, we have last but not least we have added it. So we want to avoid this unwanted guest in the house, so that is C1. Now, if you see, if I put x equals to 0, that means at point A. And where you know the slope is 0 and other quantities are also 0, right? So no degree of freedom. So that means slope is 0. So we can put 0 over here. And when you carry on with that, every term of this slope equation becomes either 0 or negative. So if you use x here, this term, like let's say which term, this term becomes 0, right? This term will also become 0 and this two terms becomes negative, right? And as the rule of the Macaulay's method, when you have negative term in your equation, you need to ignore them. Right. So in short, by ignoring these two last terms and zero value of this front two values, and then on the other hand you have zero at slope also. So C1 becomes zero in short, right? Right. So here we can say C1 is zero. Right. Now let's try to obtain the values by using the another boundary condition, that is x equals to, total is 4, yes it is 4 meters. So let's rewrite this equation. 0 equals to minus ma into 4, right, plus va into 4 square by 2 minus 63 square by 2 minus 10, sorry, 2 cube upon 6. So this will provide us an equation. Why? Because we have two unknowns here, MA and VA. Okay, so we'll keep this as one of our equations secured for further usage. So we'll keep it as it is, and we'll simplify, however, not an issue. So we can simplify these two numerical values. So let me calculate, you also calculate. Let's say 60 into 3 square by 2. So that gives you 270. Okay, so I will write down 270 right over here. This is 270. Okay, and this will be let's say 2 cube into 10 divided by 6, so it becomes 13.33. I may be slower today, but I just wanted to give you the level of understanding better. Right, that's why. Sorry. Okay, so this is 13.33. Okay, so that is what is our equational values, right? So now we are ready to develop our first equation. Let me change the color also. So 0 equals to minus 4 MA plus, here you can see 4 square and divided by 2. So it would be 8 MA, right? Minus, these two terms are, negative, so they will get added. So I think it's 270 plus 13.33, so it gives you 283.33. Yes. So now we are almost ready to rearrange this term by changing the placements, like 283.33 equals to uh, 8 times of VA, it should be VA here, right? So 8 times VA and minus 4 times MA, right? I know I'm going little out of the boundaries, but I just don't want to change this slide, because I just wanted to show you that how further you are required to use the slope equation, and that's why I'm insisting to put everything on the same page, right? So don't mind it, please. So here, slope equation, now we are going to reutilize, right? By in a way that we are not going to further consider C1. I mean, you have to introduce one another constant C2, right? So now we have one equation with us, so that we will keep this with us in pocket, right? And let's go for uh, deflection. So let's integrate it again. EI, slope will be, let us say, y, deflection will be the y again. We are reintegrating this, so minus ma x square by 2, right, plus va x cube by 6 minus 60 x minus 1 raised to cube upon 6, and minus 10 x minus 2 raised to 4 upon 24, because 6 into 4, 24, plus C1x plus C2. So now, as usual, I'll create a line over here. Don't get me wrong, because I just wanted to do it everything on the same slide, and I know that slide is little smaller than the required, so I'm just guiding you that we are moving from here to here actually. So let me draw an arrow for sequence. We are moving here right now. Okay. So let's continue. Here we have seen that we have the deflection equation, and if you use boundary conditions you will get C2 again as 0. When you put x equals to 0 you get C2 again 0, because the deflection at the fixed ends are 0 again. There is no deflection possible over here. So y equals to 0, x equals to 0, negative terms we are going to ignore, so C2 becomes 0. So now we are ready to use x equals to 4 again in the same equation of the deflection, right? That is what is our another important deflection equation. So now I'm going below and going down, so please bear with me over here. It is 0 equals to minus ma. We know that x is 4 now, so square by 2, right, plus va into 4 raised to cube by 6 minus 60 into 4 minus 1 is 3, so here it is cube now, right? It is 6, and finally 10, it's 2 because 4 is there, so raised to 4 upon 24. Now we need to simplify this further to get the similar equation out of this equation, so that we are ultimately going to solve them numerically, right, with the parallel equation method. Let's say we have another equation like this is let's say when you expand this, like all the equations like 3 raised to cube 2 raised to 4 times, divide by 24, divide by 6 here, and rearrange the term, so you will be getting equation as 276.66 equals to 10.66 times ma minus 8 times, sorry, here it is VA. So we need to use VA here, 10.66 VA minus 8 times MA. Right. So this is our equation B, right? So by using parallel method of solution of the equation, now we are forced to go to the next slide. So I am writing both the equations A and B parallel to each other. First equation 283.33 equals to 8 times VA minus 4 MA, right? And the second equation, recent equation 276.66 equals to 10.66 VA minus 8 times MA. All right. So now you would be able to see that if I simply multiply equation A with negative 2, I will be able to cancel MA out of this, right? And I'll be getting the unknown value of VA. So that is what our target is. Because ultimately, if we get the value of VA, we will be able to calculate value of MA also, right? So let's go for it, and let's multiply the equation A by minus 2, and then when you take the algebraic sum, these two terms gets cancelled, and ultimately you will be getting let's say 283.33 into minus 2, so that is uh, minus 566.66 equals to minus 16 VA. This is already plus 8, so both will get cancelled, right? And here you already have 276.66 equals to 10.66 VA, right? So that should give you minus 566.66 minus 276.66. So that is negative 290. Negative 290 equals to minus 16 and 10.66. So 16 minus 10.66 gives you 5.34. That is also negative 5.34. That is your VA. So happily we can ignore the negative signs of both sides, right? And VA will be 290 divided by 5.34. So that gives you 54.5. So that is 54.5 Newton upwards. That is your first answer that you have obtained. Now we can use this information in other equations. Say for example, any of them, like let's say in the equation A to receive the value of MA. So it is using in the equation number A here 283.33 into 8 times 54.5 minus 4 times MA. All right, so that you can use here only and you can get your answer of MA. So let's do it. 8 into 54.5, so that gives you 435.2. So this is 283. I hope you all or most of you are doing this in parallel, so you are also thoroughly involved in this 35.2 minus 4MA. Okay, so now you can get your answer of MA easily out of this equation. 283.33 minus 435.2, so that is negative 151.87 and divided by 4, so that gives you 37.96. So 37.96 Newton into meter. Answer is positive, so obviously it is anti-clockwise moment, right? So once you have worked out this, it is now easy for us to obtain rest of the forces. Now how to get reactions of the other end? Since you have one reaction with you, can I apply sigma V equals to 0? So if I have 60 kilonewton, 60 Newton downward plus 10 into 2 as another downward force and minus or equals to, let's say, VA plus VB. So can we have VB out of this? So it is 80 total, right? So 80 minus 54.5 gives you 25.6. So VB is 25.6 Newton upwards. So now you have to take moment for MB. Take moment about point B in the original, I mean simplified beam. So here we can redraw the simplified beam for your reference, ready reference. This is your VA, right? This is your MA, of which you know the value now, right? You have 60 kilonewton here, you have UDL of 10 here, you have unknown value of MB, and you have known value of VB. Right? You know the all the distances and all this and that. So let's take a moment of all the forces about point B. This is A point and this is B point. So let's write down the equation. MA goes positive, so I'll be directly using the value 37.96. Then VA, right, into the total distance. So VA is going to be clockwise moment, so minus 54.5 into 4 total length, because from A to B we are taking moment about point B, right? Then plus we have 64s and we are taking moment about this, so it will be anti-clockwise. So 2 plus 1, so that is 3, so 60 into 3, right? Then I'm taking moment of this UDL about point B, and that is also going to be the anti-clockwise positive moment, 10 into 2 into 1. And of course you have this bending moment, that is clockwise moment, so negative MB externally applied moment. And of course we cannot take moment of VB because it is on the point of interest. So clearly, evidently, it will give us the value of MB here, right? So when you simplify everything, let's take a long equation in our calculator itself. 37.96 minus, in the bracket, 54.5 into 4, bracket completes, plus we'll have another bracket, 60 into 3, right? Plus we'll have further one more bracket, 10 into 2, bracket completes. So it gives me 19.96, right? So we can say that 19.96 Newton into meter is my another pending answer. So now you can see that we have obtained all the values together, like MB 19.16, MA 37.96, VA is 54.5, and VB is 25.6. So everything is solved now, and we can draw our diagrams. So the bending moment diagram, first we will develop our basic question over here, so that we can relate it properly. Let's say here uh, two squares gives you 1 meter, 1 meter more, and 4 squares. Like let us say this is 1 meter, this is 1 meter, and this is 1, 2, 3, and 4. Okay, just to be little uh, this thing, 1 and 2. So this is 2 meter. Okay, so this is your UDL over here. All right, so we can now draw our diagram. You know that the span moments are yet to be calculated, right? You can draw the span moment, but however here we can simply draw our, first of all, the end bending moments first of all, right? And we know that MA is larger than MB, so we can draw it accordingly, and we can simply connect both the values directly, right? Okay, so this is your MA, this is your MB, right? This will be negative. Now, by using the reactions, simply you can obtain the moments about the points, right? So, tentatively, right now I'm drawing the tentative diagram. Otherwise, what you can do, you can find moment at C and then moment at D by rule of thumbs of mechanics of solids, right? So if you take moment, because you have all the forces. So for example, let me not keep it pending, let me finish it for all, because I just wanted to show you some standard cases of the friction this beam. So it is taking little more time than I estimated, but that's fine. I just wanted to show you complete solution. So VA MA, this is your point load. Here it is your UDL again. So I'm just explaining how to calculate the span moment also. So here it is point C. Okay. Okay. So cut your beam over here. Consider the equation of the left hand side. So VA into 1, because this is the distance and that is clockwise. So I will consider it negative, plus MA, that will be nothing but MC. So VA is 54 point, what's that? VA is 54.5. So it is minus 54.5 into 1, that's fine. And plus MA. MA is 37.96. So it is 37.96 gives you MC. So you will get MC as negative 54.5 minus 37.96 minus 16.54. So it is MC equals to negative, or clockwise you can say 16.54. I will write here clockwise. Right. That's it. I can show it by other ways also, or I can write down the negative value also. Now similarly, you can come here and find MD also at point D by using the same formula. And once you have the values over here, you can probably create your combined bending moment diagram. So let's expect quickly. Let's do it quickly. VA again into 2, because now it is at this point. And we have MA as usual, so that is positive, sorry, MA, and again plus 60 into 1 equals to MD here. So let me calculate it. 54.5 into 2, 109, 109, right, plus MA is 37.96 plus 60 equals to MD, right? So 60 plus 37.96, that is 97.96 positive minus 109, so that is 11, negative 11. So MD is minus 11.04, that is also going to be clockwise. So now we can spot our diagram for span moment also. Let's say this is MA, MB done already. So MC is larger than MD. So I will, come here. I will draw it like this. Then reduce a little bit, because this is 16 and this is almost 11. So should not be a large, variation. And then it should acquire the parabolic shape, because onwards MD to MB it becomes parabolic. So we can go like this. Okay. So this is what we have drawn, the combined diagram, right? So this gives you complete solution. This is the right way of doing it. This is positive, this is negative, these two values are negative. Okay, so that gives, and in addition you can definitely similarly obtain the shear force diagram as well by using the first principle of mechanics of solids. Assume that this is the simply supported beam. In that case, you should not consider the end moments, that's all. So you can go for all the values with you and draw the shear force diagrams. Like you can have the VA values, you can have VB values, and finally you have 60 and 10 as kilonewton in Newton in the force. So you can obtain your shear force diagrams as well. So I keep it with you only. You just finish the numerical in terms of shear force diagram, and I hope you have understood how we have used Macaulay's method for unsymmetrical loading in the fixed beam. So what was the crux? Like what was the takeoff of this exercise? Like takeaway, not takeoff. Takeaway for this exercise is the point I wanted to show. Say, okay, yeah. Here, this was the major point, right? Because in the earlier numerical we only ended up our calculation by using slope equation only. Because why? Because loading was symmetrical, both values of MA and MB fixed moments were equal, nearly, I mean equal itself, right? However, in this case, the moment at A, moment at B are definitely not going to be same. So we cancelled this. We cannot assume this. And that is why also we didn't started with the analyzing numerical by considering V and VB first. We kept them unknown until we received the equations A and equation B, right? And then we mutual, I mean, we with the parallel equation system, we solved them and we get our first answer. Then we went for our second unknown, and consecutively we obtained VB, then finally MB, right? So then we developed this diagram also with the help of fixed and beams moments, and then we went for the span moments as 16 and 11. So we did it. Now I'm keeping this drawing or development of the shear force diagram for your own homework. Please do it, right? And draw the shear force diagram, assuming that this beam is simply supported beam. That's all. And I'm more than confident that you will be able to do it easily because all the values are with you. So nothing can stop you in that case. And let me tell you, there will be a change in the diagram over here. So it will be a point of zero shear somewhere here, right? Somewhere in the region of C2B, right? There will be a region of the zero shear also, which you can notice. Okay, or it may get started from here also. So be careful in drawing the shear force diagram, however. So in this case, let me take it further. Like I'll be drawing some standard cases. So let me draw some standard cases. First, this color segment is misbehaving. So finally I have made it to change the color because I want black color and it's not coming up somehow. Anyways, okay, let's see. We got it. So friends, let's have a quick look on the fixed beam analysis by typical methods. There are two popular methods. First is moment area method, where you are comparing the areas of the diagrams. These are the standard cases where you can easily, happily, comfortably rather use that technique. This is point load, this is UDL. If you wish, you can combine them together for combination of forces, point load and UDL also, provided that this point load is in a center. So then there are other possibilities of similar loading, like symmetrical loading. Let's say equidistant equivalues point load. These two values should be also same and the distance should be same. So in most of this type of cases, you can definitely obtain your or you can obtain your fix and moments and other reactions by using area moment method. But when you have any sort of unsymmetrical loading, for example this one, right? Do not waste your time in deriving the area moment equations and all this. Just go for Macaulay's method and start developing your equation. It will give you a better solution in less efforts and more accuracy. So if this is the kind of numericals that you come across, why I am sharing this with you, you can draw these things in your notes. You can allow, allot whatever values you want to give to this problems and develop your own problems, right? Generate your own numericals. Let us say like this. So when you have partial UDL, you know smartly how we can work. We can spread this UDL fictitiously on the entire span like this by extending this further and reapplying the opposite UDL like this, and your life becomes more comfortable by developing the equation for plus and minus UDL. However, it's up to you how comfortable you are with the concepts. But today, just now, we have seen that even it is completely mesh up of the forces in any conditions you can develop it. Now, further, even if I apply one more complexity, you should be in a position to solve them. However, we expect that the moment area method, moment area method as well as the Macaulay's method. Right. Both are very well known to us. We have practiced them as possible as we could. Now it's again a game of the practicing. So you practice more, you can win any race. You can obtain all the values. Once you have the values, I have also explained you how to convert them into the diagrams, because getting the values of fix and moments is not sufficient if you want to fully analyze the given beam. So if it is an instruction that obtain the fix and bending moments, then you can stop here. But if it is said that draw the shear force and bending moment diagram for the fixed beam, then you have to go for span moments also, and you should draw the shear force diagram as well as, right? So practice accordingly, that you are always required to draw the SFD BMD for the complete beam, right? So in the next session, I shall be showing you how to analyze continuous beam, and then let's see if required, we'll go for the mesh up session where we can have some this type of one of this type of numerical, then we'll have some this kind of numerical, and finally one more numerical for the continuous beam. So now continuous beam we shall be using in the next session, in the next week. And the intention behind taking the continuous beam is to show you the method of consistent deformation. See, do not get confused, because I have noticed that similar structures are being analyzed in the other counterpart where Tarak is taking the lectures, where he is also explaining the same type of the beams with different analysis methods. So that is why I would advise all of you to do not get mix up with your concepts. That's why I am taking less numericals and more explanation, so that you can clearly understand which method you are following. At the end of the day, suppose if you have fixed and beam in front of you with a central point load, you are completely free to use whatever desired method you want, whether you want to use it slope deflection method, whether you want to go for the typical Macaulay's method for fixed beam, or even moment area method for fixed beam, or even consistent deformation. So I understand it's little confusing, but do not get confused. It's very simple that the method with which, see, in examination, there are two possibilities. One is the method of the analysis will be asked to you that only analyze this beam by this particular method only, or in the second case you will be free at your end to utilize method, and that in that case any method with which you are comfortable you can use that method, right? So I'll be stopping here today for this session. You rush to the next session, and in the next week we'll meet again with the understanding to be developed on consistent deformation method, and then we'll enjoy some other numerical exercise as well, right? So thanks again, thank you very much for joining this session. Keep practicing, develop your own problem statement, and try to apply the methods which we are sharing with you, right? So thanks again. Be safe, take care. We'll meet again in the next class for consistent deformation method. Thank you.